Probably not really, because you just probably hear me. They might hear you. So the first thing is that if you look at your equation sheet, there's some astronomical data there. And I was looking at it last night, and it's not quite good. So I have some little addendums. I've also posted, if you go to lessons, Unit 1, and then Universal Gravitation. I've posted the astronomical data there, and I'll just give you guys a copy as well. So instead of using the one that's on your equation sheet, you can just staple this one to your equation sheet. Okay? So the second thing is, let's try this question here. An isochronous or geosynchronous satellite of the Earth is one that stays above the same point on the equator of the Earth. Estimate the height above the Earth's surface needed for such a satellite. Hint, what other satellites of Earth do we have good R and T measurements of? Okay, so remember, K is the constant, R cubed over T squared is constant for any satellites orbiting Earth. So give that a shot right now. So the problem is there's no numbers. I just gave you a bunch of astronomical data. What's the satellite that orbits Earth that we have good astronomical data on? The moon.
Oh.
Yes, the moon. The moon is a satellite, yes. A satellite is anything that orbits either a planet or a star. You can call it. The Earth is a satellite of the sun, for example. So what's the R value of the moon as it orbits the Earth? 1.74 times 10 to the 6, and that's in meters. And what's its period of the moon as it orbits Earth? Pardon? 27.3 days. Okay?
Wouldn't we take the radius of orbit?
The radius of orbit?
Yeah.
Yes, the mean radius.
Yeah, not the radius of the object.
So you want the mean distance from sun, but if you notice on this for the Earth, or sorry, for the moon, there's an asterisk and it says distance from Earth.
Oh, I didn't see that.
So that's the mean radius of the moon. So that's how if you were to draw the moon, that would be what we just did there. So yeah, this is not what we want. We actually want, yes, 3.84 times 10 to the power of 8 meters.
What do I name this?
This is universal gravitation.
What's the me?
Me, that means moon to Earth.
Okay.
Because we're going to have other ones, right? So what's the question asking? What's the height above the Earth's surface? So you can imagine here's your Earth. All right, and this is the moon. And here's our satellite. Oh, it's freaking out. Gotta love that. So this distance here, the distance from the center of this Earth to the center of the moon is RME. So the question is, we'll call this one just R. What's R? So R, we don't know. And what's the period going to be for the satellite if it's geosynchronous or isochronous? So that means it stays above the same position on the equator of the Earth. So what's the period going to be? 1 day, correct. Okay, do we have enough information now?
Yeah.
Right? What are we actually looking for, though?
Height.
Height above the Earth's surface, right? So we're looking for, we'll call this H right here, this height. H. H. All right, and then what's this value here? from here to here.
Is it on the sheet?
What would you call this? What's this circle thing that I've drawn?
Earth.
Earth?
Yeah.
Okay, and Earth is represented as a circle. So from the center to the outside is the
Radius.
of the
Earth.
Earth.
Oh. This is.
All right. Radius of the Earth
Well,
is right here.
it could be the radius of the circle.
So you could say that R is just the height plus the radius of the Earth.
Where do we get the height?
The height is what we're looking for.
Oh.
That's how high it is above the Earth. Okay, what do we do now?
So.
How? What do we know about Kepler's third law? Things?
Period squared.
So, what does it say? R cubed over t squared is constant, right? It's always the same?
Because you gotta cube the R and square the T.
So, if this is constant for all satellites of a certain object, then if we look at the moon, so the radius of the moon to Earth cubed, it's a terrible 3, over the period of the moon around the Earth squared will equal what we've called R over T, so R cubed over T squared.
It says T squared divided by R cubed equals
It doesn't matter.
that.
You can flip them.
Okay.
Yeah,
Okay, because that's what I do on
Oh, 'cause
it's fine. Yeah. Oh, shit. Oh, that pulled everything, didn't it? Oh well. Okay, what's R? It's up here.
H plus RE,
Right? And what's T?
1 day.
1 day. And then we have the other two values, right? So we could have H plus the radius of the Earth cubed equals T squared times the radius from the moon to the Earth cubed over the period of the moon around the Earth squared. Sure? So you take the cube root of both sides. And then just subtract RE from both sides.
So do you cube root it and then minus it or minus it and then?
You need to cube root first because the addition is within the brackets, right?
Okay.
So when you plug all those values in, you should get something like 36 kilometers.
Where'd you get the T times RME over TME squared?
Where did I get the T?
Like that, right part of that equation right
Where did I get
here. Oh, right
this?
there. Yeah.
So that comes from this equation here. Right? I'm just solving for this thing. Right? But this thing
Oh, right, okay.
is that.
Yeah.
Okay? Okay, you guys try number 2. 36,000 kilometers. 36,000. So this is times 10 to the 3 kilometers. 3.6 times 10 to the 4 kilometers, or 36 times 10 to the 3 kilometers. Yeah. So the period of Venus is 0. Around the sun. 61 years. The period of Earth. What's the period of Earth?
27.
Don't look.
1 year.
1 year.
Are we going in years or days?
You could do days. The problem is with the Earth, you got to go 365.25 because of the leap years,
Oh, I guess.
right? Or you can do it years, and then in which case it's 1. Okay. The mean distance from the sun to the Earth, or the distance from the mean distance from sun for Earth is 1.50 times 10 to the 11 meters.
Where did you find?
And the distance from the sun to Venus is 1.08 times 10 to the 11 meters. So this is from the data that we know, but we want to figure this out. So from the sun to Venus, using Earth as a reference. So for the guys away, we know this, this, and this, and the answer should be this. Okay, so we need to calculate this. Okay, guys, so you should have the distance from the sun to the Earth over the period of the Earth is equal to the distance from the sun to Venus over the period of Venus. And then when you solve for the period of Venus, solve for the distance from Venus to the sun, you get the cube root of the period of Venus squared times the distance from the sun to the Earth cubed, all over the period of the Earth squared. And when you plug the values in, 0.6615 years squared times 1.50 times 10 to the 11 meters cubed, all over 1.00 years squared. Brackets around those. And take the cube root. And you should, in fact, get 1.08 times 10 to the 11 meters.
That's awesome.
Okay, so using the information for Earth, you can find the period of the Earth in terms of seconds, because you have the period of the asteroid in terms of seconds. And you just need to solve for the radius of the asteroid about the sun. And you get this thing here. Plug in your values, and 2.81 times 10 to the 11 meters is the answer. Okay, guys, let's move on to Newton. So, like we saw the other day, that Newton said the force of gravitation between two objects is inversely proportional to the square of the distance between them. What he also figured was that it's proportional to both masses of the objects. So if you have object 1 and 2, they have mass m1 and m2, then the force is proportional to m1 times m2 over r squared, where r is the distance between them. Okay? So then, if they're proportional, you can make them equal with a constant. Okay, and that constant is called big G, not little g, big G. Big G. It's the universal gravitational constant, 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared is big G. So then force is equal to, no longer proportional, big G times m1 times m2 over r squared, where big G is the gravitational constant, m1 is mass 1, m2 is mass 2, both in kilograms, and r is the distance between m1 and m2 in meters.
So this big G's on here, it's on the back.
Big G is on the back of your equation sheet under constants. Big G is a small number. It is much smaller than little g, which is ironic. Okay? So you're going to be using this equation a lot. You're going to be using this constant a lot. So get used to them. Any questions on that? All right. So what does that say? If you have two planets and one of the planet's mass is doubled, then that doubles the force between them, right? Because if you think about the equation, then you get 2F equals G m1 2 m2.
So it's linear because of the goal.
Yes, it's linearly proportional to the masses. So if you double the mass of one of the planets, you double the force between them. If a planet's twice the distance from the sun, or it's twice the distance from the other thing that's affecting it gravitationally, then you get 1/4 of the force, right? Because force, again, G m1 m2 over r squared. So if you increase this distance, if you double it, then you get 2r in there, right? So you have G m1 m2 over 2r squared. 2 squared is 4, right? So this is actually 1/4 of the force now, because this becomes G m1 m2 over r squared with a 1/4 in the front. Right? Okay. If both masses are doubled, the force is 4 times as strong, right? 2 times 2 is 4, so 4 times the force. And if the distance from the sun is halved, again, because of that square factor, if you halve the distance, then the force is 4 times as strong. So,
Half is just divided by 2.
yeah.
Just double check.
Right, so if you have G m1 m2 over 1/2 r, and we square it, then we get G m1 m2 over r squared times 1 over 1/4, which is just the same as 4 times G m1 m2 over r squared. Right, so it's 4 times as strong. Okay? So the first one, guys, calculate the gravitational force between a 60-kilogram woman and an 80-kilogram man standing 10 meters apart and 0.3 meters apart. Go ahead. So here's the answers for A and P. Just apply this equation. Okay, number 2, guys. Astronaut, 65 kilograms, walking on the surface of the moon, whose radius is 1.74 times 10 to the 3 kilometers, and the mass of the moon is 7.35 times 10 to the 22 kilograms. What is the weight of the astronaut? So that's the force the moon puts on the astronaut, is the weight.
We have to convert that to meters, correct?
Yeah, convert it to meters. And your answer should be 105 newtons. Five newtons.
I'm off by about a million.
You're off by 1,000,000. Okay. Well, that's because you need to change this to meters.
That's why I'm off by a million.
We'll
Yeah.
see what happens.
So when you square it, it gets off quite a bit.
That's why I'm off by a million.
Well, if 105 million units is going to do. That's sick.
Stop
Pull that
mentioning
out of
that.
your
just asked what happened. Roll of shame.
Okay, so again, you just need to apply that equation. Number 3, guys. You have a hypothetical planet with a radius 20 times that of Earth and a mass 100 times that of Earth. What's g, so little g, near its surface?
That would just be the force.
No, little g, the acceleration due to gravity.
So it's not going to be 9.81.
Nope, because it's not Earth anymore, right? It's a hypothetical planet who is, it will not be 9.81.
Force equals that mass times acceleration. F equals ma.
Or mg, yeah. So you'll have F equals mg, which also equals gm times the mass of the planet all over the radius of the planet squared. Your m's are going to cancel, and you find your g value. Okay, and your answer should be 2.46 meters per second squared. Make sure your units are correct. Are they correct? What's the units of big G?
Meters cubed divided by seconds.
Newton times meters squared over kilograms squared. And it's going to be multiplied by kilograms from the mass of the planet and divided by meters squared. So the meters squared will cancel. Kilograms will cancel with one of those kilograms. We get, this is newtons per kilogram. And a newton is defined as a kilogram meter per second squared. We divide that by kilograms. And we are left with meters per second squared. Okay, for the next one, guys, calculate the effective value of g, the acceleration of gravity, at 3,200 meters above the Earth's surface and 3,200 kilometers above the Earth's surface. So you need to, your r value, say for A, your r is going to be the radius of the Earth plus 3,200 meters. And for B, your r value is going to be the radius of the Earth plus 3,200 kilometers. Okay, and you're going to do the same thing. You'll get g is big G times the mass of the Earth over r. Okay, so go for that.